Greetings everyone. I am with you today with another project, but in an online environment, because this project doesn't really have lab components. We all did it, by computer-based simulations and computer-aided design tools. So let me not hold you in wait longer, and just show you my project. So here I just opened Cadence. I will just open Cadence here. Hopefully it won't take a lot of time. And while it's opening, let me just go over it very quickly. This semester, in the context of my analog CMOS IC design course, we have designed a digital to analog converter as a project. We also did a lot of other things. We designed a lot of op-amps and such. But a piece, the resistance of a class is always its project. So in this video, I will mainly be talking about the project, the design procedure of the project, debugging, and the many results we got from the project. So let's start, shall we? Hopefully you can see Cadence right now, and I'll just open my library and go to my project DAC. So let's start with the schematic, because there are actually some things I want to go over in the schematic form. As you can see, we have a classic R2R network and a buffer op-amp, a DAC architecture, where what's the challenge in designing that? It's a standard topology after all. Well, I will, in the next 5 minutes or 3 minutes or so, I will tell you all about the challenges in the design. Let's go over the op-amp first. I wouldn't say simplest, but our most essential components, definitely. The most fundamental, I want to say. So as you can see, we got a PMOS differential input stage. Well, input stage is always differential in op-amps, that's not a surprise. But we are using a PMOS input stage because we want our DAC output to go to accept common mode inputs as far as low as 0, and well, it cannot accept as far as high as supply voltage, but it actually can accept 4 volts. We are using a 5 volt supply here. It can work in 4 volts, so we actually have a wide input common mode range. But as I said, the choice of the input transistor types are due to the low input common mode voltages we desire. You can also see a nice simple resistive biasing circuit here. Well, we could have used a more complex biasing circuit like a constant current source biasing, but for our design considerations, this was actually better and more flexible. And well, it is actually more simple, and simplicity can be a nice advantage, and sometimes even a resilient advantage in our design. So of course, when the supply changes or the temperature changes, the supply current here, the reference current here will change. But the question is not whether it will change or not. It is how much it is going to change, and will it affect our actual operation in our operating range. And for this design, it was easier to apply a current source such as this rather than a constant current source that actually worked in our operating points, our design corners, let's see. Then we got a classical second stage, classical current source load amplifier here, and then we got a class B output stage. Well, why use a class B output stage? That is because we want rail-to-rail output from our op-amp. We want the output to go as far below as 0 and as high as, well, we actually want it to go as far as 4, but going as far as 5 isn't a disadvantage. As you can see, actually, the Miller network isn't connected to the third stage, as it is sometimes viewed to be the standard to connect the Miller capacitances to the third stage, because the gain from the first stage to the third stage is the maximum gain. Well, it is not here. We could actually do that. We could turn this gain stage to a negative gain, add a current mirror here to make this positive gain, and then this is already negative gain. So in that case, you would have negative gain from here to here. In our actual setup, we have positive gain here to here, so you can't add a Miller. But if you wanted to get the gain advantage from the totality of these two stages, we could do what I just said and get a negative gain from the first stage output to the third stage output, and add a much smaller Miller capacitance. Actually, I tried this and it works with 5 picofarad Miller capacitance rather than our 20 picofarads. But the disadvantage of that topology here is that we are using a class B amplifier. And in this case, when the input of the third stage goes to 0, actually one of the transistors here, and specifically, let me see, actually, when this goes down, this goes up. So yeah, one of the transistors here, when this is lower, the PMOS, and when this is higher, the NMOS, will go out of saturation. And actually, the effective gain at the third stage will decrease considerably. So actually, connecting the Miller capacitance to the third stage can hinder our stability at common mode input corners of 0 volts and 4 volts. So we didn't do that. Another debugging we did in this. Well, let me show you the results first, then I will talk about the debugging procedures. Well, as you can see here, hopefully, we get a nice low offset voltage, which means high DC state gain. And this is actually important because offset voltage affects the accuracy of our DAC. We get a high open loop gain, and when we actually test with a load circuit, at our worst stability corner, which is 2 volts for our design, we got 56 degrees of stability, which is quite nice indeed. And when we tested the input common mode range, as you can see, op-amp continues its linear output from 0 volts up to 4 volts when we change the common voltage from 0 volts to 4 volts, which is real nice. And actually, we also checked for the output impedance of our op-amp, which was actually, as you can see here, this is the output impedance measured at 1 kHz over the entire common mode voltages, and it is consistently lower than 1.5 ohms, as you can see here. Oh, actually, this is measured at 1 MHz, not 1 kHz. And one interesting thing here is the step response, one thing we should talk about. As you can see, as I mentioned before, we had quite acceptable stability amounts, but during our step down procedure, we are getting this weird jolt up before we go actually down. Well, this was the main debugging challenge for me actually in the op-amp design case, and let me talk you through the solution of that. The problem was caused by the low quiescent current in the second stage. So let me demonstrate you what happens when the circuit, when the input goes from high to low. So this node goes from high to low, right? Which means this transistor is fully open and there is a lot of current going through there, which means this gate voltage will go higher, which means this transistor wants more and more current to itself. Well, but our circuit cannot instantly respond to that. So this this transistor at 5 volt is still at 5 volts gate voltage, and it is actually still closed. So where could it draw its current from? Turns out it actually draws its current from this stage through charging this capacitor and then onto itself. And if this stage, if M7 doesn't have enough quintessent current, the voltage here in the second stage will go down, and as a result of this is just an inverter, the output voltage will jolt up before it comes down to satisfy the current needs of this transistor and to charge this capacitor. So what we did to solve this problem was to increase the size of this transistor, which solved it. And as you can see here in my second report, when we look at our step response, I'll just show you that. As you can see here, we don't have those jolts. At the step down cases, you might have noticed we have a little bit of offset overshoot here, but that is because we are testing the circuit in this case at worst power corner, so some stability is lost there, which is natural at worst power corners. So let me continue through our op-amp analysis. And actually we also did noise analysis. Well, this is no longer op-amp analysis, but the basic DAC analysis. As you can see, we have constructed the DAC here, and I will talk about the specific design considerations of the DAC very shortly. As you can see, our noise figures actually come as quite expected. We have some shot noise coming at low frequencies, and we have white noise. Well, you can't actually characterize as white noise as it is combined together with the shot noise, but whatever. We have constant noise at higher frequencies. And the noise figure, the noise density, let's say, at 1 kHz is 9 nanovolts per square hertz. And we also characterize the PSRR of the power supply rejection ratio of our op-amp and the DAC. This is the PSRR of the DAC, and I actually inverted the PSRR. So it is output over supply rather than supply over output. As you can see, it is quite high actually at low frequencies, but we actually care about PSSR at higher frequencies because, you know, our noise figures, like noise coming from the digital parts of our circuit, are usually higher frequency, but we actually have, you know, quite acceptable 40 decibels, give or take, PSSR, power supply rejection, which is good. So that was the inverted PSSR, by the way. So it is not the effect of supply at the output, but it is the effect of output at the supply, let's say, the inverted one. So the values come up nice and positive. You will I am careful at clarifying this because you will actually see the uninverted version quite soon, because the standards can kind of change between reports. But anyway, you will see it. Then our design moves on to the DAC portion. We already talked somewhat about this. I showed you the noise and PSSR figures of the whole DAC. But let's talk about some specific design considerations now. When it comes to the DAC, there are several choices to make, design choices to be made. One is the values of these resistors, and the other is the width of these transistors. Well, let me talk about both of them actually. Well, the average value of these resistors basically determines two things: your monotonicity. If your resistors are higher, you will have better monotonicity, and monotonicity means, you know, when you go from 0, 1, 1, 1, 1, 1, we have 8 bits of input, so imagine I just said 8 bits. From 0, 1, 1, 1, 1, 1 to 1, 0, 0, 0, well, the circuit, if the resistances are not well aligned, if they are not exactly equal with each other, the output may not go up, it may go down, or it might not go up at the same step as you expect. For instance, we have a 4-volt range 8-bit DAC here, so at every step we have 256 steps, and at every step we expect our output to move up 15 millivolts. So if you don't have good monotonicity, it might just move up 5 millivolts, or it might not move up at all, which is a big problem. If you choose larger resistances, you get more noise, but you actually get better monotonicity because the discrepancies, the relative discrepancies between individual resistances are decreased. We are not using an absurdly large value here. 5 kilohertz is a reasonable value, and we are actually able to make it in reasonable lengths in this process. You can see a length of one resistor is on average 21, 22 micrometers. So it is quite reasonable. It is quite compact for our process. I will come to the differences between these resistors and these resistors in a moment here, but let me first talk about the transistors. Well, if we were designing an ideal DAC, we would want our transistors to be ideal switches. But unfortunately, for the designer, no switch is ideal. And as you can see here, we are using transistors for our switching. We are not actually using full transmission gates because for the high switching portions here, we know the source will always be connected to high, so we can comfortably use CMOS, and for the low switching portions here, that switch to be low. We know that the source will always be at the lowest voltage, and we can comfortably use only NMOSes. Well, one non-ideal characteristic of these transistors are their on state resistances. So when I actually turn this resistor on, or this one on, it will add a resistance to this net as a whole. And the differences here you can see are actually to compensate for that resistive change. Well, you might ask me, quite rightly so, aren't the resistances of PMOS transistors, on-state resistance of PMOS transistors and NMOS transistors different? Well, the charge mobility in p-dop regions and n-dop regions, at least for our process, are different. So you are going to get higher. If you have the same width and the same length, you are going to get higher on-state resistance for PMOSes and lower on-state resistance for NMOSes. I actually discussed this with a professor recently, and he told me that in modern processes, such differences are not like, well, there is no difference with charge mobilities for modern processors, but we are using a fairly old technology here. We are using XFAB 0.6. It's a fairly simple technology, but it is suitable to learn a lot of things from it. Well, anyway, because of the charge mobility difference I just mentioned, most of my peers actually went ahead and used bigger PMOSes and smaller NMOSes. Well, because when you do that, you can equalize the resistances, and then you can compensate with a nice value here that accounts for both transistors, and your monotonicity will come out quite nice. Well, there is one problem there. That arrangement does not really account. It accounts for the resistances of the transistors, but it does not really account for the capacitances, the off-state capacitances the transistors bring into our ideal design. And if you make the sizes quite different, so you must make the PMOS device as big as NMOS nearly to get equal resistance. But then what happens is the off-state capacitance of the PMOS is end up quite higher than the off-state capacitance of the NMOS. And what happens is when the state changes, the PMOS cannot transfer all of its charge to the NMOS, so it actually discharges over the resistive network and creates current spikes at our input, and these current spikes can be quite significant at our most significant step, at our worst step, so 0111 to 1000, because all of the transistors are changing state at the same time, so there's a lot of current flow here if the capacitances are not equalized, and you are going to get a very large current spike, which your op-amp tries to smooth out, but it actually can't because it is so large. So I actually didn't went for a wider PMOS, narrower NMOS arrangement. I actually went for quite the opposite, to equalize the capacitances so that we don't get current peaks. And after all, the resistances, we are not using the process minimum widths here, so the resistances we get from the PMOS and NMOSs are not that huge, and we can just add the average resistance here at to compensate for the resistances that are not connected to transistors, and just get quite nice monotonicity actually, because the resistances are not that large absolutely. They might be different from each other, but they can still be compensated by using an average equivalent resistance. So having talked about that quite extensively, let me actually show you the response of our op-amp, not op-amp but the DAC, when you actually take the digital inputs. Here I have a test bench for that. So here is the counter test bench, and now I will show you the response when you actually make the inputs count from 000 to 11111, 8 bits gradually, and I will show you the response now. So here's our input counting, as you can see, and here is our output response. As you can see, it is quite linear. It covers the whole range we want, and more importantly, we don't have any current spikes at any step. Here you can see just a minute spike at the worst step, but that is somewhat expected, and it actually doesn't go really over the next step. So the spike is smaller than one step, so it is neglectable, and we get a nice smooth linear response from it. Another thing is we did corner analysis for our DAC, so we tested worst power corner with highest supply voltage. Our nominal supply voltage is 5 volts. We defined worst power as 5.25 volts, and the process worst power conditions from cadence corner analysis. Here is the step response for the worst power condition. As you can see, our circuit is still stable because it isn't oscillating or anything, and it actually has a neglectable overshoot at the step up response. And we also tested the worst speed case, of course. For the worst speed case, we actually get quite a slow circuit. Worst speed case is defined at 4.75 volts at the appropriate temperature. We would actually expect the worst speed state to be at 0 degrees centigrade, but for some reason, I don't actually know the specific characteristics of this process, but in our software analysis at least, the worst speed case would always come at 50 degrees centigrade, which was weird. Anyway, here are the worst speed conditions, and actually at the worst speed conditions, our conversion rate, maximum conversion rate, comes near 2 kilobytes per second. Well, I must remind you, like, actually at the burst power case, it is more closer to 1 megabytes per second. So the nominal circuit will have something between these two values, and I expect that if we did a Monte Carlo analysis on this parameter, on the conversion rate parameter, we would actually get a quite acceptable speed, more closer to 1 megabytes rather than 2 kilobytes. I think the 2 kilobytes is quite an extreme value there. Anyway, continuing on, these are just the power standards on our circuit. Let me mention that in transient loads, our current I must have a table for that here. At transient loads, at nominal conditions, our current pulls up to like 22 milliamperes from a, I think, 5.25 volt source. And at nominal DC operation, it pulls just 7.8 milliamperes. Well, at worst power condition, the situation of course worsens, and it changes according to how we define worst power. You would expect worst power conditions to come at 50 degrees here, but as you can see, they come at 0 degrees here, and at those conditions, our worst power current consumption at steady state is 13.8 milliamperes, and during transient switchings it is 34.6 milliamperes. Now continuing on, this is the first step, and actually we did a Monte Carlo analysis, changing process parameters randomly for our monotonicity. So we expect, as I said, 15 millivolts of increase at every step, and the step that is most susceptible to changing this value is the first step, 0, 1, 1, 1, 1, 1, then to 1, 0, 0, 0, 0. And when we actually change process parameters, we can see that our circuit still keeps its monotonicity. So the mean value is 17 millivolts, a bit higher, but the minimum values do not go below 13 millivolts and 20 millivolts, which are quite acceptable. So we can certainly say that, well, I don't want to be, well, leaving humility aside, we can say that, most of our chips produced with this design will actually have acceptable, passing monotonicity values. So that is quite nice. Another aspect that we ran Monte Carlo analysis on was the PSRR. You can see the non-inverted version of the PSRR. So supply's effect on the output. The changes in the the small signal changes in the supply's effect on the output. Let me put it clearly that way. And we did a Monte Carlo analysis at the 1 MHz PSSR. As you can see, it is coming here as 40 decibels. It is quite nice. And the Monte Carlo analysis showed that it did not really go below minus 30 decibels, which is quite acceptable. And when it slants towards the lower range, which means the supply changes will have lower effect at the output, which is quite nice for us. And that was the detailed analysis of our DAC. Finally, let me show you that we have constructed is the wrong word there. We have designed the layout for both our op-amp. Here you can see our op-amp layout. Just a moment there. For both the op-amp, let me show you the lower view. This is the op-amp layout design. As you can see, I put quite some time into this to make it work nicely. And well, design considerations here are to make the differential input stage symmetric, of course, and to save space, and to make resistances coming from our connections neglectable. One design consideration is the op-amp is a source resistance for the transistors, especially the current uh, source transistors here. And as you can see, their source resistances are scaled down with the actually. So when we scale transistors up in width or in gate values, we must scale their source resistance down if you want to have same source voltages. The transistors with higher widths will have higher currents, and if they have the same resistance at their source, they will have, well, in our case we are using PMOSes, so they will have lower source voltage, which is not something we desire. So we must adjust our resistors accordingly. So as you can see here, for this biasing circuit, the one with the smallest width, we have just one connection. Here we have actually three larger connections. This has the 5 times the width of this. And we have the side connections here, which actually don't do much because they are limited by these connections here. And here, which is actually this transistor, which is actually twice has twice the amount of width compared to this transistors. I am talking total width here. It has actually 6 of the same connections here compared to 5. So this is going to have the half of the source resistance, which will mean it has the same source voltage. We can actually see that in our DC analysis. We actually extract the circuit from this design and run another analysis. I will just show you that in a moment. And then let me show you the layout design of the DAC. Here at the lower view, as you can see, our designs are quite compact. Actually, this design is, let me see, 520 micrometers to 450 micrometers, which is quite small. Even in IC design standards, I have seen much larger IC switch designs. Well, but it is a simple design. But when I worked on RF designs, a chip size was standardized to, something like 1.5 millimeters by 1.5 millimeters. Anyways, there are some important design considerations here actually. As you can see, we have split the voltage sources for the digital part of our circuit and the analog part. So when the digital part draws high currents from the supply in transient switching portions, our supply of our op-amp doesn't get affected, so the op-amp output doesn't get affected. And to prevent the same thing in the ground portion, we actually made a star ground. This is our ground pin here. We actually made a star ground connection here. So the currents given to ground or taken from the ground by the digital part of our circuit does not go through the ground connection of our analog part of our circuit. And as I said, we actually extracted these designs and ran some tests on them. So let me show you those tests now actually. So here are our designs. They have quite nice areas, as you can see. Let me show you the tests now. So as you can see, we have run LVS and we're not getting any errors. So here, we actually, to my surprise, we actually lost some gain and stability when we extracted parasitic resistances. Our stability actually fell down to 40 degrees, which is not quite nice. But one nice thing is we still have high gain bandwidth product. my first op-amp design was a folded cascade that had gain bandwidth product of like 60 megahertz, and this design has 100, 113, 14 or 15 megahertz depending on how you round it. So I am quite proud of it, and if this rate of increase continues, I should be able to make gigahertz amplifiers quite soon. Gigahertz gain bandwidth product amplifiers quite soon. Well, actually, I have a theory about the gain and stability loss here, but I did not have enough time to test it. I think it is due to some resistance between the Miller compensation circuit here and the input transistor here, the second stage input transistor here. But I think it is due to that, but I couldn't have time enough to test it, unfortunately. Continuing on, well, actually, well, the decrease in stability, decrease in phase margin and gain are unfortunate, but it actually didn't affect our design's operation standards very much. Due to the decreasing of the gain, we have higher input offset, but it is still acceptable because it is lower than our step value. Our step value, as you will remember, was 15 millivolts, so that is actually quite lower than that. And as you can see, our op-amp is still linear when the common mode is swept from 0 volts to 4 volts, so we are also still successful at that. And when we look at our worst step, which is indicative of all our other steps, we see it has somewhat of a higher overshoot. That is expected because our stability dropped. But one important thing here, hopefully you can see the small marks, up and down marks here. These are actually due to clock cycles of our digital circuit. As I mentioned, our digital circuit draws power, draws high currents during switching times, which create noise at our op-amp. But as you can see here, our op-amp is actually not quite affected. Our output is not quite affected by the noise. Those noise jumps are quite neglectable, in fact. So that was a design success for us. And our monotonicity step is still at an acceptable 16 millivolts. And we actually run our PSSR, and our PSSR value is actually improved here. As you can see, at 1 megahertz we were getting minus 40 decibels, and now we are getting minus 50 decibels, which is quite nice here. So our supply will impact our output even less, which is quite important in this mixed mode circuits, as I mentioned. Well, those were all of the points I wanted to cover for today. Thanks for listening, and I hope we meet at another project soon. Goodbye. Well, it actually takes some time for me to close the stream, the recording. And I don't plan to edit it.